In this final video, we're going to work with computing flux using the divergence theorem. If we have a rotation field, our divergence will be 0. If I take a general vector field F is equal to A cross R, where A is a vector with components -1, -1, and 0, and R is a vector with components -y, x, and z, our cross product gives us a vector with components -z, -x minus y. When I take del dotted with F, I get the partial with respect to x of -z, plus the partial with respect to y of -z, plus the partial with respect to z of -x minus y. In each case, the terms are 0, and my net flux is 0. Let's work an example. I want to find the net outward flux of the field given by F is equal to a vector with components z minus y, x minus z, y minus x, across the boundary of a cube that is given by the set of all points x, y, z, such that the absolute value of x is less than or equal to 1, the absolute value of y is less than or equal to 1, and the absolute value of z is less than or equal to 1. Don't panic too soon. Compute del dot F. This is equal to the partial with respect to x of z minus y, plus the partial with respect to y of x minus z, plus the partial with respect to z of y minus x. In each case, they're 0, so that my net flux across the boundary is 0, because this was a general rotation field. So let's work another example, but this time with a vector field that's not a rotational field. I want to find the net outward flux of the field given by F is equal to a vector with components x squared, 2xz, and y squared, where S is the surface of the cube in the first octant, defined by the planes x is equal to 2, y is equal to 2, and z is equal to 2. I take del dotted with F, and I get the partial with respect to x of x squared, plus the partial with respect to y of 2xz, plus the partial with respect to z of y squared. This gives me 2x plus 0, or 2x. Now I can compute the triple integral over d of the divergence of f dv. This is equal to the triple integral over d of 2x dv. The boundary in the first octant is from 0 to 2 in each of x, y, and z, which means that the limits of my triple integrals are from 0 to 2 of the integral from 0 to 2 of the integral from 0 to 2 of 2x dx dy dz. This is a straightforward integration problem, and I get 16 for the net outward flux on this particular field. Everything we've done up till now has assumed that my regions were solid in R3. Now I want to consider a region D that consists of all points inside a closed oriented surface that I will call S sub 2, and outside of a closed oriented surface I will call S sub 1, where S sub 1 lies completely within S sub 2. The boundary, which is simply connected, consists of S sub 1 and S sub 2. If I sketch it, I have a three-dimensional object, S sub 2, that encloses a three-dimensional object, S sub 1, inside of it. You'll notice that my region S is everything inside S sub 2, but outside of S sub 1. Letting n sub 1 and n sub 2 be outward unit normal vectors for my surfaces S sub 1 and S sub 2 respectively, we'll notice that n sub 1 points outward from S sub 1 but inward into S sub 2, while n sub 2 points outward from S sub 2. This means that the outward normal on S sub 1 will be negative n sub 1. Now let's suppose that my vector field satisfies the condition of the divergence theorem on a region D bounded by two smooth oriented surfaces S sub 1 and S sub 2, where S sub 1 lies completely within S sub 2. We'll let S be the entire boundary of D, meaning S is equal to S sub 1 union S sub 2, and we let n sub 1 and n sub 2 be outward unit normal vectors for S sub 1 and S sub 2 respectively. This means that the divergence theorem for hollow regions will be given by the triple integral over D of del dotted with f dv, which is equal to the double integral over S of f dotted with n ds, which will be equal to the double integral over S sub 2 of f dotted with n sub 2 ds minus the double integral over S sub 1 of f dotted with n sub 1 ds. So let's work an example here. I want to compute the net outward flux for the vector field given by f is equal to a vector with components x, 2y, and 3z, where d is the region between the cylinders x squared plus y squared is equal to 1 and x squared plus y squared is equal to 4, where z lies between 0 and 8. Del dotted with f gives me 1 plus 2 plus 3, which is equal to 6, so that my triple integral over d of del dotted with f dv is simply 6 times the triple integral over d dv. This means that my net outward flux is going to be the difference of the volumes of the two cylinders. The triple integral over d of del dotted with f dv is equal to 6 times 4 pi minus 8 times 8, or 144 pi. Notice that I didn't actually have to go into an iterated integral here. I simply needed to interpret what the triple integral over d dv was going to give me, and then I had a simple method for finishing the problem. Now you get to try it. Pause the video and compute the net outward flux for the vector field given by f is equal to r times the magnitude of r, which can also be expressed as the vector with components x, y, z, times the square root of x squared plus y squared plus z squared, where d is the region between the spheres of radius 1 and 2 centered at the origin. When you're ready, restart the video to check your understanding. The first thing I want to do is compute del dot f. Del dotted with f is equal to the components of the del vector dotted with f given by a vector with components x, y, z times the square root of x squared plus y squared plus z squared. This is equal to 4x squared plus 4y squared plus 4z squared over the square root of x squared plus y squared plus z squared. I'm going to simplify that a little bit by factoring a 4 out of the top and using properties of exponents to express my rational term as 4 times the square root of x squared plus y squared plus z squared, which is simply equal to 4 times the magnitude of r. The triple integral over d of 4 times the square root of x squared plus y squared plus z squared dv becomes the iterated integral from 0 to 2 pi of the integral from 0 to pi of the integral from 0 to r of 4 rho squared sine u d rho du dv, where I've converted the integrals into spherical coordinates. I compute from the innermost integral out, and what I'm going to get is the flux over a sphere with a radius of r. This gives me the integral from 0 to 2 pi of the integral from 0 to pi of r to the 4th sine u du dv. This gives me the integral from 0 to 2 pi of 2r to the 4th dv, which is equal to 4 pi r to the 4th. This is the flux for a solid sphere. The net outward flux for this problem is going to become the difference between the flux for a sphere of radius 2 and a flux for a sphere of radius 1. In other words, 4 pi times 2 to the 4th minus 4 pi times 1 to the 4th gives me 60 pi for my net outward flux. This is how we can apply my divergence theorem in computing outward flux for objects that are either entirely solid or that may be hollow. There is a lot more we can do with both Stokes' theorem and the divergence theorem. There are some great applications available to you in the homework and in the book that really help you understand and cement the reasoning behind these theorems and the power of having them in our toolbox. There's also opportunities when you're working with these ideas to involve symmetry, and we're seeing how we're using some of that already. Be sure and let me know if you have any questions about working with Stokes' theorem, the divergence theorem, or anything else we've done in multivariable calculus. Thank you for letting me be part of your journey in mathematics. I hope you enjoyed the class.